started. Well, I'll start by thanking everyone here for joining us for this session. In this session, I'll be sharing how at Pinterest we took the journey of performing high-performance AI, specifically with Apache Iceberg and Parquet. And okay. So this is the agenda for the session today. We'll start with the most important thing, just to get some credibility from you guys, the scale. The scale of data and the scale of business at Pinterest. Oh, sorry. We'll do the overview of like the data infra at Pinterest and the various lingos that we'll be using for the rest of the slides, like what are features, what are signals, and then we'll talk about 4 challenges related to data scale, specifically for machine learning and AI, which is evolving features, joining features, and rapid iteration, and we'll end it with the row-level operations, why that is relevant and important. Okay, so scale. As a company, Pinterest has over 600 million monthly active users. We have over 1.5 billion pins saved every week, and more than 10 million votes. Now, more relevant to this session here is the data scale. And we have more than 500 petabytes of data, more than 100,000 tables, which are Hive and Iceberg tables, more than 20,000 machines that operate Spark and Root clusters, 1,000 plus nodes for Trino clusters, and every day we have over 400,000 jobs that run compute. Okay, so at Pinterest, our mission is to inspire users to curate a life they love. To achieve this, we rely on state-of-the-art recommendation and ads model trained on tens of petabytes of data over the span of multi-months of engagement logs. These models drive personalized recommendation, showing users the content that they actually want to see or is more relevant to their interests. These models are significantly improved, or they perform better when they are trained on large amount of data, usually spanning multi-months of engagement logs. Our ML models are trained on wide range of features, including pins, users, advertiser level data, the session-based features. So everything at Pinterest, which helps us build these models, are essentially coming from engagement logs, but eventually they take shape of features. This is a very high-level overview of the infra that powers the machine learning and AI at Pinterest. All of our data, they somehow make their way to data lake, which is on S3, AWS S3. And on top of that, we have Hive Metastir, Apache Iceberg, and Apache Gravitino-based catalog. And then we have catalog services where we do things like data IQ that Jack talked about, which does the compaction and other value-added services. And on top of this is what we have, where we have the data sets, and these could be just the raw data, could be the incremental data, or even the process data, which is then processed by various batch and streaming processing platforms, namely Apache Spark, Trino, and Ray. And on top of this, and anything above the batch processing and stream processing, we typically call them as big data platform. Anything on top of that is where the machine learning platform comes in. So we have something called feature store, and what is a feature? I'll talk about that in the next slide. But a combination of a lot of these features, and we have like millions of features, is what together is known as Galaxy. And from these features, we build the machine learning data set store, which is then used to perform the model training and model serving. Okay, I've mentioned the word feature a lot of times. So let's see what a feature is. A feature is, for example, it could be a user information, it could be a pin information, it could be location, it could be a group of these things. And a feature is essentially what is a relevant set of information that together provides some signal or insight into user behavior. And if you think about how this is laid out, typically we have a lot of galaxies, and each galaxy is essentially a table. And for those who are familiar with Parquet, each column family is what we refer as signal, and each column becomes individual field or features. Now, by looking at that, and we have a lot of galaxies, and each galaxy can have like 10,000 features or columns in it, or in some cases more than 10,000 even. And these columns, they grow very rapidly. Our machine learning engineers, our data scientists, they think that like, okay, this could be a new additional insight-driven feature, and then they would add that. Or in some cases, they'll say, oh, adding this didn't help much, so they'll remove it. So on a day-to-day basis, there's a lot of columns that are being added and being removed, and that is where we have to talk about evolving features. Features and columns are added, removed very frequently, to the extent that like we have some of the tables which have easily over 10,000 columns. And removing and adding columns in Hive, especially in 1.2, didn't have that good support of like adding and removing columns. So one option back in the days was that, okay, we'll just null out the columns and we will keep on adding new columns. That works okay, but when you have very large number of columns, very wide tables, that doesn't really scale. The schema becomes unmanageable, Parquet footer read cost increases significantly, and even storing nulls can be very expensive. And whenever I say that, like, people are like, oh, so Parquet is a columnar data. If the column is all null, it can get run length encoded, so why are we worried about storage there? So let's actually look at how Parquet stores data. In Parquet, the nested structs and nests are stored in a way that like it has the value, but also stores something called repetition level and definition level. And the value is dependent, or the value of a cell is dependent on the parent level. For example, if the parent can be nullable or not. So even if a column is always null, each row can have different repetition and definition value depending on its parent. And this causes an overhead to store, encode, decode the value. So this was all theoretical because we knew that we have a lot of nulls and we kept on adding new columns. We knew that like, okay, our storage size is increasing, but it didn't make sense because like we were just adding nulls. So we did a bunch of profiling, and what we saw was there was a significant impact, cost impact of these nulls. There was a lot of performance regressions when doing full table scans where we were reading a lot of these nulls on white tables. In some cases, the cost was like just almost double the V code if you're using reading the null columns as well. The storage regression was significant as well. And we did some profiling, and we saw that like up to 50% of time was being spent on the repetition and definition level reads, which kind of makes sense because even if it's null, you are still going to read the repetition and definition level. And similar observations were made on the right side. So because of this, Hive in general didn't work well for us for our machine learning and AI use cases where we wanted to keep on adding new columns and removing the old columns. And that is where Iceberg helped us significantly because it allows you to add columns, remove columns without affecting the old data thanks to the versioning of schemas. So that's one use case where Iceberg and Parquet kind of came together to help us meet one of the key ML requirements. The second use case I'll be talking about is the feature backfill. So as we said, machine learning engineers constantly add and remove new features. Then the models, the production models evolve based on a bunch of A/B test results. A traditional way for a machine learning engineer to add a new feature is called forward logging, where engineer will come, they will add a new feature, and then they will wait for the data to accumulate. And because, as we said, these models perform well when they are trained over months of data. So in practice, they would have to wait for like 2 to 6 months for the data to accumulate and then be able to tell, oh, whether this new model is good or not. The other problem with this approach is that the same pipeline between production and experimentation is being shared, which is never a good idea. Then to overcome this problem, what we started doing is we started in feature backfill. So what we would do is we would counterfactually compute historical values and join with the production training data to back populate the feature values. Now the benefits of doing so is that we are not waiting for any data to accumulate. There's a cost of computation, which we'll talk about. There's a very definitive isolation between the production and the experimentation pipelines. And it essentially gave more confidence to the machine learning engineers to experiment a lot more because they knew they are not going to affect the production models. But the problem that we mentioned is the cost, the cost of the computation that we'll be doing upfront to do the joining. So this is what it looks like. We have a bunch of features in something what we refer as the Galaxy feature store. And then if we have to put a new feature, we can add it to a custom data store. And for every new feature, what we'll have to do is we'll do a mass join between all the existing features and the backfill data with the pre-computed data for the features, and all of them together. We'll go through a mass shuffle to do the join. In terms of Spark, they typically do the sort merge join, so they have the huge expensive step of shuffle. Now, this shuffle was very, very expensive. To give you some idea, these jobs or backfills would run for weeks. And the shuffle was the most expensive part of it. And to add to the concern, if we were to do some new machine learning engineer comes in and they want to do another experiment, they will add on to this shuffle, and then there are more data to be shuffled, and then this is petabytes of data that's getting shuffled around. By the way, the petabytes of data that's on SC is very well compressed, but when it comes to memory, it sometimes blows up to 8 times. So that there's a massive data explosion. So to avoid this, what we did was we started supporting something called bucket join. And what we essentially did was we made sure that all the feature data sets and the machine learning, the training data set, they are all bucketed by the same bucketing scheme. And with that, what happens is that there is a agreed upon mechanism or understanding that all the data sets are going to be distributed in this fashion. And with that, there is no shuffle required. So different executors would come up and they will choose a decided upon bucket and then start reading from the sequence sheet. With this, we were able to avoid expensive shuffles by using the storage partition join. It helped achieve 65% cost savings in the backfills, and also increase the iteration by 90 times compared to the forward logging approach. We took a step further on this path, and we thought that, okay, why, if someone is experimenting, do they really have to go and do the materialization of the data into a final training data store? If this is going to be a one-time thing, they might as well just read it, decide, build the model, train a model, and then look for its quality. So for that, we started supporting. We have the custom readers which will read from multiple features and then do the join on the reader side itself. So this will avoid the materialization completely. Saves on the cost, saves on the all the garbage that gets collected otherwise, and also increases the speed. We added this feature on Spark, Trino, and Ray. For Spark, this was mostly backward from 3.5, but for Trino and Ray, this was all done in-house. So with that, by choosing Iceberg, we were able to do the bucket joins, but then there were additional benefits too, because we were now doing the bucketing and then the local bucket sorting, so that we are able to do joins on the reader side. Our data was getting compressed much better. In some cases, the compression improved by 4 times. And because we are writing Iceberg, we were able to utilize the versioning. And so we were able to write with better concurrency. Multiple machine learning engineers can come in, they can start writing their data, and all of them can happen in parallel. And so there was a big win to the velocity. We were able to utilize the write or publish mechanism to make sure only the verified models are pushed to the production and not causing any accidents because of a bad model getting pushed to production. And very importantly, we were able to support a better rollback because again of the versioning. Okay, so far like the two use cases we talked about are mostly from the machine learning side of things, but data scientists have a huge role to play whenever it comes to the model training and model taking it to production and deciding which one passed the test. And that is where the rapid ideation comes in. So typically for rapid ideation, all the data scientists what they do is like they use sampling. Like sampling is a very well-established notion where you would go look at the data sets and you'll just sample, pick a percentage of the data set and do your training and compute on top of that. Because it's just a fraction of the data, it's cheaper and it's faster too. Now with machine learning though, it's kind of very important the order in which you use the data to train your model. If you use the same data but like you randomly read the data, the trained models can behave very differently. So for this reason, the use case for the sampling kind of differed for machine learning and AI use cases. What we needed was a reproducible way where we can do the sampling and be able to do the joins. Because like if you are joining two sample tables, there's no guarantee that there will be a common key between the two. But in in our use case, we have the requirement that we will have to make sure that like if we are joining between the two sample tables, we should be able to see the same keys. So this definitely didn't meet the requirement, wasn't built into any of the existing systems. And so we kind of built a sampling mechanism on top of Iceberg buckets. So in this one, what we did was like we utilized the Iceberg bucketing and then also used the sampling push down mechanism that most of the compute engine supports. And with this, we were not sampling at the row level, we were sampling at the bucket level. So instead of saying that, oh, out of like a million rows, I want like 1,000 rows, we will say that, oh, out of like 500 buckets, I'll sample just one bucket. So, but when we use pick one bucket, we pick the same bucket across all the tables that we are joining with, and that's how we were able to guarantee that the key space is common between all the tables. We added the support to Spark and Trino, and the speedups were great, like as expected for a reduced data volume. This is just a screenshot showing that like a very large query, which usually runs for 4 to 40 seconds, was able to finish in 12 seconds. But more importantly, from the data science perspective, the variation between the actual versus sample wasn't noticeable. So this was great for our data scientists and their ideation speed. Okay, so this was for the data scientists. And last, I'll end with the one use case where most of our business level people, the compliance teams get very worried. And that's the row-level operations. And row-level operations is something that became very relevant when all the compliance, like the user data deletion requirements came in. And so in machine learning use cases, like we still had to meet those requirements where like if a user comes in and requests for deleting the data, then we'll have to make sure that none of the models are trained with their data. Now to do that, we had to make sure that like we are deleting the user data, and this is just an example, deleting the user data from raw logs all the way to the process data to the end models. And to do that, we had an old system that would essentially go rewrite the entire data set. But you can assume that doing that at petabytes scale is super expensive. So what we did was, like, again, this is where we utilized Iceberg, is we use the Iceberg copy and write delete mechanism. Now, the good thing with copy and write delete mechanism is that you don't have to rewrite all the files, right? You would only rewrite the files where the data needs to be rewritten. That sounds great in theory, but then in practice what we saw was that almost all the, because like initially the data wasn't like really bucketed or sorted, so all the files were getting touched upon when we were rewriting or performing the deletions. So we introduced some mechanisms to improve the efficiency. So there were two things we did. One was we started sorting the data that wasn't sorted, but doing that for all the data sets, that's super expensive. So we only did so when we are performing a deletion, at the input step, we'll see if a file is already sorted or not. If the file is sorted, we don't do anything, we just treat it as is. If the file is not sorted, only then we would sort it and then perform the deletion. So there was an upfront cost for unsorted files to get sorted, but this upfront cost kind of like dwindled down for a period of time to the point where like today we don't have any unsorted data, and whenever we have to perform deletions, it's like super cheap compared to the previous system. With that, we were able to scale deletion capacity by like 10 times, reduce the storage cost because of the better compression of achieved through sorting by 30%, reduce the processing cost because we were processing less data during deletions by 30%. Overall deletion jobs runtime reduced from weeks to days, and because the jobs are running for a short period of time, there were less chances of failures. Overall failure rate also reduced by 90%. Okay, so that was all. I think I'm on time.
Thank you. For the deep dive into how